Thanks for either joining this talk in person or watching it online. So in this talk, my name is David Wajc, and in this talk I'm going to tell you about joint work with Chrstos Papdimitriou from Columbia, Tristan Pollner from Stanford, and Amin Saberi from Stanford. So the title is a bit of a mouthful, so I'm not going to actually read it. We'll just kind of point out some key terms. So we're going to study some bipartite matching problem in an online and stochastic setting. And I'd like to make this kind of a case for studying these online stochastic problems beyond the classic profit inequality approach to considering these problems. So if some of this jargon doesn't make sense, everything will be clear shortly. Let me quickly start with the problem definition. All right, so a simplified version of the problem we study has the following bipartite matching market. So we have houses on the one hand and buyers showing up over time. And in particular, at time t, buyer t will enter the market with some known probability pt and make a take it or leave it offer of VT dollars for any house in some subset that he cares about. So think about, maybe you're interested in one particular housing district, but you don't care about, there's no distinction between the houses otherwise. So all of these probabilities and values and neighborhoods are known a priori. So maybe this buyer shows up at time one. And, based on their values and what we know about the future or expect about the future, we might decide to sell them the second house. Then another buyer shows up, the second house we can no longer sell her, but maybe we could sell her the third house and we decide to actually wait for later for a more lucrative buyer. Then time step 3, maybe buyer 3 could show up, but maybe also, with probability 1 minus P3, they don't show up. So we cannot sell them any of the house, and so on and so forth. Okay, so what we'd like to do is kind of maximize our revenue despite lack of knowledge of the future. So here are a few things that are known about this problem. So we already know a number of 1/2 competitive algorithms for this problem, and I'll give due credit in a slide. So what do I mean by competitive algorithms? These are algorithms whose expected gain is at least 1/2 the gain of a prophet who knows the future. Okay, so this falls into this rich and illustrious literature of profit inequalities, starting in the late 70s with the seminal work of Krengel and Stochastic, who gave the first profit inequality for a single item. So just, selling one house. This has been generalized any which way to, multiple homogeneous items, matroid constraints, matchings, and so on and so forth. And as you guessed from the previous slide, that's the last one is going to be the focus of this talk. Okay, good. So we know 1/2 competitive algorithms for this problem. And by the classic lower bound of Krengel and Stochastic, this is the best we could hope for. So let me maybe briefly review this. So here we have 2 buyers. One buyer shows up with probability 1 and has value 1. And the second buyer, who may or may not show up later with probability epsilon, has a significantly higher value of 1 over epsilon. Okay, so any online algorithm, of course, can make at most $1, either sell to the purple buyer or wait for the blue, but an expectation they're getting at most 1. Whereas an offline algorithm just sees the realization of the randomness ahead of time and says, okay, when this guy shows up, I'll actually sell to him. I'll get $1 in expectation and 1 minus epsilon from the purple in the remainder of the time. Okay, so 1/2 is the best you could do, and we know how to do it. So why do I need another, 15 minutes of your time? So let me maybe revisit the term best possible marked in yellow here. So again, what we're talking about in the previous slide was profit inequality. So comparing with an all-powerful, all-knowing prophet who knows the future, which is great if you can get some positive results, but this is really not the kind of information we're privy to. So this does not feel like a fair comparison in some sense. So what we'd like to do instead is compare to a different character, which we'll refer to as the Titan or online optimal algorithm, who is maybe all-powerful, so computationally unbounded, but similar to us, does not know the future. So does not know the realization of the randomness. Okay, and this makes for a more apples-to-apples comparison and also allows us to get more nuanced comparisons between online algorithms. Okay, so let me briefly tell you what's known about online optimum or what's kind of natural. So we can compute the optimum online policy for whatever input you actually care about using standard dynamic programming techniques. Unfortunately, for this problem, this would the natural dynamic program would take exponential time. Okay, for some simple cases, we can do it in linear time. For example, for a single item, the classic optimal policy you can easily compute in a linear time dynamic program. And so the question we're asking here is, what is the complexity of computing or failing that, approximating the optimum online algorithm? Great, so we have 2 results. So the first is, we come bearing bad news. So obtaining the optimum online algorithm is likely impossible, and actually even approximating it within some universal constant bounded away from 1 is p-space hard. Okay, so barring any surprising complexity theoretic results, this is a non-starter. I'll point out that this is the first hardness result for computing or approximating the optimum online algorithm for any online Bayesian selection problem. So I think there's room for more results in this vein. On the other hand, we also have a positive result showing that there exist polytime online algorithms which approximate the optimum online algorithm within a factor strictly greater than 1/2. And if you remember, 1/2 is the best you could hope to do when you're competing with the optimum offline algorithm. Great. So I'll point out that in the paper we have a much more general problem than studied in this, short talk. But this should give you a flavor of what's going on in this work. Okay. So in the remainder of my time, I'm going to give you a flavor of what's going on in theorem 2. And if you're interested in more details or in finding out what's going on in theorem 1, I urge you to read the paper, or just reach out and ask. All right. Cool. So let's start with a simple 1/2 competitive algorithm as kind of a warm-up, which will motivate what we're going to do later. So let's consider the following ex post offline LPs, which upper bounds the expected value of opt-off. So here you can think of xit as being the probability that house I is sold to buyer T by the optimum offline solution. So naturally, we're trying to maximize our expected revenue. Every buyer cannot be sold with probability higher than the probability that they enter the market. And no house can be sold with probability greater than 1. And finally, since xits are probabilities, they're non-negative. Okay, so let's take this LP real quick. Let's solve it, and let's use it in the following algorithm due to Ezra et al. From last year's EC. So at time t, if buyer T enters the market, remember this is a probability PT, we pick a single house with probability xit over PT. And if you look at constraint, this would be constraint 1, good. If you look at constraint 1 and sum over all i's, you'll find that this, the sum of these probabilities is at most 1, so this is well defined. I can pick at most one such house with these marginal probabilities. And then if this house is unsold, for some reason the animation's not working, cool. If this house is unsold, then we'll match this house and this buyer with some correcting probability. And I urge you to not look at this exact expression for a minute. Okay, so as it turns out, there's a fairly simple 3-line analysis of this algorithm, or at least kind of giving the gist of it. So the key lemma is the following. The matching output by this algorithm matches each edge IT with probability exactly xit over 2. Okay, and this, of course, will give us what we want by linearity, and we'll revisit this in a minute. So here's the 2-line proof of this lemma. So a corollary of this lemma, if you go by kind of an inductive hypothesis, inductive proof, you'll find that the probability that I is unsold at time t is exactly 1 minus summation over all the previous t primes, xit prime over 2. Now, this is, again, a kind of a funky expression, but if you notice, this is exactly the denominator of this qit, which I urge you not to look at not too long ago. Okay, and this is great. Now everything's kind of going to cancel out nicely. So what we get is the following inductive step. The probability that I sell house I to buyer T is exactly the probability that this buyer enters the market, picks house I, this house is unsold, and then we actually accept this transaction. Okay, now if you look at this not too carefully, you'll notice that almost everything cancels out, and what we get is exactly xit over 2 as claimed. Perfect. So if you didn't follow this, it's not too crucial. Just kind of take away from this algorithm is 1/2 competitive just by linearity. We get 1/2 times what this LP gets by linearity, and that upper bounds 1/2 times opt-off. Great. So unfortunately, we know that 1/2 competitive is all we can hope for. So we need some new ideas if we want to break 1/2 when comparing to the optimum online algorithm. So let's start with one new idea, which is a slightly stronger LP, which will bound online up. So we came up with this new constraint, which apparently was known in the literature. So here's credit where credit's due. And the observation is the following. So here's, let's focus on some edge IT, some buyer T and house I. For this edge to be matched, we need 2 events to happen. The first is that, well, the buyer has to actually enter the market, otherwise there's no one to sell to. And the second is that this house needs to not have been sold before time T. Now, the crucial observation here is that for online algorithms, events 1 and 2 are independent, right? An online algorithm cannot make its choice of whether or not to sell house I before time T based on whether or not T shows up, because it just doesn't know this information, okay? And notice that this is not true for the profit, for offline algorithms. If you remember the example where the lower bound example from earlier, you'll see that that's exactly what it was doing. It was correlating these choices with future arrivals. Okay, so this insight will prove useful. So if we want to formalize what we get from this, we got the following. If we abuse notation from earlier and let xit be the probability of edge IT being matched by the optimum online algorithm, then this probability is at most the probability of t showing up times the probability of I being available, which is exactly this expression here at the bottom. Okay, good. So what can we do with this? So first of all, for a single item, this additional constraint plus the constraints we saw before completely characterizes the optimum online algorithm. So you can solve this LP and use it and round it losslessly in an online fashion to get exactly one approximation of this LP, and so one approximation of opt-on. For a number of houses, of course, we know that we can't expect something so good since it's p-space hard to approximate, but this constraint turns out to be useful for approximating the optimum online algorithm. Okay, good. So I'll point out again, Torrico and Torriello use this for something of a heuristic, and we actually use it to give provable guarantees for online algorithms. Okay, so this is the LP we get, all the constraints we had before, plus this new constraint in orange. Great, so let me briefly outline our new algorithm, which will be a modification of the previous one, plus the ideas that go into the analysis. Okay, so we again start by solving this LP, now including the orange constraint. And we'll start by following essentially the same steps with a slight change of parameters. So again, at time t, if the buyer arrives, we pick a house with some probability. If it's available, we'll sell with some correcting probability. And here I really ask you not to look at the exact expression. Okay, so quick observation, if QIT is less than 1, then a simple proof by induction shows that we get exactly the marginal probabilities we'd like, which is something strictly greater than 1/2 times xit. And throughout the talk, I'll have, I'll use epsilon instead of say like 0.01 or something, just to kind of convince you that, for epsilon small enough, things should work out. Okay, small enough, but still greater than 0. Okay, so if QIT is less than 1, then we get the marginals we'd like, and we would obtain an approximation of 1/2 plus epsilon. But as it turns out, if QIT is 1, then we might get something a tiny bit less than 1/2. Still kind of in the ballpark, but a tiny bit lower. So 1/2 minus say like 3 epsilon times xit. Okay, and our approach to fix this and increase the marginal probability, thank you, increase the marginal probability of I and T being matched is just repeat all this text in yellow for all houses I which have QIT equal 1 if buyer T was not matched. So if they weren't sold any house. Okay, good. So here's a rough idea of what's going on. So here's a naive approach for this. So what we said before is the probability of a house being sold to a buyer as a first pick is roughly 1/2 times xit. A simple calculation which I'll spare you shows you that the probability of the buyer not being matched to its first pick is about 1/2. And so you might naively think, okay, for a house to be sold to buyer T as a second pick, we need to not have matched T, so that's with probability 1/2, and then this kind of same process we had before, which succeeds with probability 1/2 xit. So we should get like 1/4 xit. And for small enough epsilon, 1/4 is definitely greater than 4 epsilon, right? Okay. Unfortunately, what I'm saying here is bogus, so please don't commit this to memory. And as it turns out, what I'm implicitly assuming here is that the probability of house I being sold to buyer T as a second pick, conditioned on T not being matched as a first pick, is essentially the same, or at least as high as its probability of being matched as a first pick without conditioning on anything. Okay, but this turns out to be false, and let me kind of hint at why it's false. Okay, the animation got broken there. So here's a few problems. Let's say that house I is picked with probability close to 1. And in addition, this QIT equals 1. So what does this mean? This means that when buyer T shows up, they will most likely pick house I. And then if we don't match the two, so if T remains unmatched, well, that's precisely because I was previously sold. And so picking again is not going to increase the marginal probability of I being matched. So let me kind of recap what I'm saying here. Conditioning on T being unmatched is essentially equivalent to conditioning on I already being sold, which will make this yellow expression here actually be pretty darn close to 0. Okay, so that's problem number 1. And we have the same kind of problem if the different houses' sold statuses are strongly positively correlated. If I tell you that buyer T picks some house J and this house is already matched, if it tells me that all the houses are matched, then I'm just not going to get anything from trying to rematch it to house I. Okay, so let me give you a brief idea of how we address both of these issues. So the first is as follows. If you unbox this QIT from a few slides ago, you find that if this expression is equal to 1, then the probability of I being picked is actually pretty darn small. Okay, and here we're crucially using this new constraint. I'll save you the algebra. Second crucial observation is that the sold status of these different houses is weakly correlated. So maybe there's some positive correlation, but not too high. Okay, and here's the rough outline of this. What we show, thank you. What we show is that these statuses, we can rewrite them as the sum of two different Bernoulli variables. And we show that these, so AI and plus BI, we show that these AI and AJs are negatively correlated, or even negatively associated for those of you who are into probability. And the second thing we show is that these BIs are actually low probability events. So if you plug all of this into the additive law of covariance, simple manipulation shows that the correlation between SI and SJ cannot be too high. So what I'm saying is, if you tell me that T tried to match to someone and this person was already sold, then this doesn't increase too much the probability of somebody else already being sold. And so the second pick should basically help me. So quick recap. Let me maybe spare you the general gist of it, but all I'm saying is that the probability of being matched as a second pick is the probability that T is not matched, and this probability of being picked conditioned on T not being matched is basically the same as being picked as a first pick up to some 1 minus epsilon terms. Good, so putting all of this together, we get something for the probability of being picked as a second pick. We got almost 1/2 for being picked as a first pick. Putting everything together, we get our desired 1/2 plus epsilon. So putting all of this together, we get a 1/2 plus epsilon approximate algorithm for approximating the optimum online. So I know Anima showed me 2 minutes about 2 minutes ago, but let me briefly take maybe another minute of your time. So quick recap, we showed that approximating optimum online within some universal constant bounded away from 1 is p-space hard. On the other hand, we can approximate it in polytime and in an online setting better than what we can approximate the optimum offline algorithm. Again, we have more general results in the paper. Let me briefly point out some natural open questions. Generally, how well can we approximate the optimum online algorithm? Okay, so for this problem we saw today, there's fairly large gap between upper and lower bounds. We know that it's at most, 0.999999, and I could go on for a while, and at least 0.51. So there's quite a large gap there. Generally, we could ask about other online Bayesian selection problems or all your favorite online stochastic problems. So any flavor of Markov decision processes. Quick case study, which I think is particularly appealing, is matroid constraints. So for the single item problem, we know a 1 approximation. So that's 1 approximation for a uniform matroid. In EC of 2 years ago, was 2 years or 3 years ago? 2 years ago, Anari et al. Gave a p-task for bounded depth laminar matroids. Don't worry about the exact jargon. And the natural question is, can we get a similar p-task for arbitrary matroids, or is this, on the other hand, p-space hard or something similar? All right, so I think that's all I had. Thank you for your time, and I welcome any questions here or afterwards.